So we're looking at one more way of finding the centre of gravity, this time just using a couple of scales. What I'll do first, let me just quickly review the different ways you can try to measure the centre of gravity practically. So we're going to learn a lot of mathematical ways to do it, but we'll have a look at some of the practical ways of doing it. Let me just get rid of a couple of these layers if I can. Yep. So the first way we talked about, I did it with a foam box. I think it was my old phone box covered in duct tape. But you can put a roller underneath, and I've used this in the past for when doing some earthquake testing. So just give you a bit of background on that. And so what we do is we test these HVAC units. So that's heat and ventilation units. And so what we do is we put them on a vertical shake table. So this table here, it's got a ram underneath, so the hydraulic ram underneath that shakes this up and down, and we use it to test whether these things will survive an earthquake or not. So one of the issues with those is that inside they're quite complicated. So that's the inside of this unit. So it's got some filters that pass water through them for cooling the air, and it's got pumps and compressors and all sorts of things inside it. And so you can't just assume that the center of gravity is in the middle of the box. You've got to actually find out where it is. And so one way you can do that is just the same as what I did with the phone box, the little box I had when I was showing you on the video earlier. You can just put in there, let me just see if I can find the right layers. Interesting. Yes. And so you can put a roller underneath. So this is just representing the piece of equipment we're testing. So put a roller underneath that. This is the roller here. I need to select that layer. Sorry, I don't use this package very much. But you just put that underneath, a roller underneath it like that. And then you just roll this backwards and forwards until you find the balance point. And then, just as we did before, you then know that your center of gravity lies somewhere on that plane. Then what you do is you swap it around. Let me just see if I can find the one. There we go. So then you swap around, got another roller underneath the other way. Then you know the center of gravity is somewhere on this plane. And what I'm interested in is, or when we're doing this problem, what we're trying to do is to find the center of gravity on plan. So let me just see if I can find the right layer. So what we want to do is we want to find, if we're looking down on top of this, we want to know, and we found those lines with the rollers, center of gravity is here somewhere. And so I want to find the center of gravity on plan like that. The reason we want to do that is because we're going to put this on top of the shake table. Just bring this in a bit. So we're going to put it on top of the shake table. Just get this flat. And so what could happen is, so this is the shake table, so you get your table like that, the ram underneath, and it doesn't have any supports other than the ram itself. The ram is holding everything up. And so if you put the center of gravity in the wrong place, and suppose your center of gravity is here somewhere, then the force from that unit is going to be coming down here. You're going to have a reaction from the ram over here. So just as we were talking about before, when we're talking about resultants, you've got a lever arm, so you've basically got a couple. And so therefore you're ending up getting a moment. And what that moment does is it puts a strain on the rod for the hydraulic ram. So that rod's moving up and down to shake the table, and it'll wear that out on the sides where it runs through some bearings. And so we don't want to do that. So we want to find out exactly where that center of gravity is, so that we can make sure that we're putting it square onto the table. So that was the first way of finding a center of gravity. Just put a roller underneath, roll it backwards and forwards, find the planes, and then do it in another direction, find an intersecting plane, and then you can figure out where exactly that center of gravity is. Obviously, we can't find the height of the center of gravity because we can't turn this on its side and roll it sideways. Usually you've got quite a stiff base, but the sides usually aren't very strong. But for this, it doesn't really matter where it is height-wise. You just have to make sure that you're putting it on the correct place on plan. So that was those. see if I can turn all that stuff off. Interesting. Excuse me. Try and find them all to turn them all off. Come on, disappear. There we go. Okay, the second way of doing it was to hang the object. Let me bring this round. So what we're doing then, so you hang this object one way or another, and then what will happen is, let me just see if I can get this to work. Not on the right layer, maybe on that layer. Why is it not showing me my dotted line? There we go. So this will then, if you hang it from a particular point, it'll rotate around until it finds its balance point, might be around there, and then you know that the center of gravity must lie somewhere on this line, because it'll always rotate around until the center of gravity is underneath the support point. Then you would find another point, so you would choose another point to support it from, and you would attach it from there. And again, it would rotate around. Sorry, I'm not very good at choosing my center of gravity. So it would rotate around until it found its balance point again. So then you'd know the center of gravity must lie on this line. What do I need to do? Get rid of that. So the center of gravity must be under the support point. So now you've got two lines that cross, so you know your center of gravity must be in here. And you find your center of gravity. So one other way we can find a center of gravity is to put a couple of scales on it. So this one here was the one where this is this beam that we used as a testing rig. So we used it for a test rig down in the labs. It weighed about a couple of tons altogether. The issue we had with that was we didn't have much headroom. So the lab is not all that high. We were lifting it this way. The little head was downwards. And so when we were putting it in position, we didn't have much space between the hook and the beam. And so usually you would want to, if you did have a bit more headroom, you'd usually have your hook up here and you'd bring your slings down to lift it up. And that way it's not quite so critical where the center of gravity is. You can kind of move the hook back and forward along the slings until you find that right point. Because we had so little headroom, we needed to, the hook was always needed to be quite close to the beam, so we couldn't really use big slings, so we could only really attach at one point. And so to make sure it rotated flat when we lifted it up so we could get it into position, it actually sat on top of a couple of rams as well. So that it rotated, we needed to make sure that this center of gravity, the point at which we lifted it up, was exactly under that hook. So we had to make sure we had a lifting point here. So what we needed to do was work out the center of gravity. What I actually did was I've made a model of this in Inventor. So that's one of the drawing packages. It does a lot of other things as well. Inventor, it's quite a handy package, software package. But failing that, what we could have done is just get a couple of scales. So it could be load cells or scales, just something to measure the weight of this beam. And so that's what I'm imagining here. So we put the scales underneath and they're reading out the weight. So although it's reporting in kilograms, it's really measuring the force, it's measuring the weight. And so we've got a couple of reactions here. So we've got I'll just draw those on. And I'll actually I'll change them into newtons, a bit more correct for engineering rather than showing kilograms. So 1200 kilograms, 1.2 tons, that's 12 kilonewtons. If you assume gravity is 10, so roughly 10 meters per second squared. And this one over here, that one is 8 kilonewtons. So what we can do now is the stuff we'd done previously. We can find where the resultant force would be. So we could choose any point to do this around. We'll do it around A. So what we'll do first is we'll figure out the resultant force. So sum all the y components in this case. We'll probably take y upwards, just make everything positive. But we have to realize that if we were to imagine this, just delete this one. So just tidied that up a little bit. So, yep, we're finding the resultant. We need to find its position, and then we're going to use the fact that the resultant is going to go through the center of gravity. That's what the center of gravity means. So we could replace these two supporting forces by a single force, and it would balance at that point. So we've only got y components. So let's have a think about, so there, just let me get the right pen. So therefore, we're going to have some resultant going through a point. So let's just call it r. R, the value of r, the magnitude of r, is just going to be simply add up f of y. We don't have any of it f x's. So therefore, we're going to have 12 kilonewtons plus 8 kilonewtons, which is equal to 20 kilonewtons. So that we know that the magnitude of r is going to be that. Just going to move this across a little bit and just move things around just to keep things tidy. Now, so we could replace these two forces with a single force r. We need to know where it's applied, so we're going to look at the moments of these two forces about the point A. Could have chosen the point B, but we're going to take it about A. So the sum of the moments is equal to, so we've got, let's call this F1, call this F2. So it's going to be F1 times the lever arm to F1 plus F2 times the lever arm to F2, which is going to be 12 times, now that's got no lever arm, there's no moment associated with that because that force goes through the point A. Then for F2, we're going to have 8 times 6. So the total moment is going to be times 6, it's 48 kilonewton meters. So that 6 is in meters and the force was in kilonewtons, so it's 48 kilonewton meters. Then we're trying to find, well, where is that r going to go? So we know that r is equal to 20 kilonewtons. Let me just draw it out of the way first. So we know that r is 20 kilonewtons. I'm not doing any of this to scale. Just changing the thickness of that. It's going to be r equals 20 kilonewtons. We don't know where it is at the moment, but what we can do is we've essentially got a reaction force and a moment about A, so we can figure out the position that R would need to be in to create this moment. What I should have done was just also write down the direction of that. And so it's this moment here, 8 times 6 is going this way, so it's anti-clockwise. So it's this way, and R is going up the way and it's going to be going in the same direction, so that's going to work out fine. So R times the lever arm to the reaction is going to be, has to be the same, has to be that 48 kilonewton meters. That means that R was 20 times that lever arm dr must be equal to 48 kilonewton meters. So dr must be 48 divided by 20, which is 2.4 meters. Just checking back through that to make sure I haven't done anything silly. It looks okay. So we know that the 2.4 would be about here somewhere. So that's where so we know that that's where the resultant is. The resultant's the balance point. And so what you're basically saying that this force could replace these two forces. So you could have this just balancing on this force at that position. It also means that the component of the weight goes through that point. And so our center of gravity must be here. And so therefore, just checking what the question was asking for now. So the center of gravity must be 2.4 meters from A. Done. Cool. Next problem.